Dear students, in previous video we were talking about the EMF series. Now EMF series you know well. Now in this video we are going to take some revision of the Nernst equation. Dear students, what is Nernst equation? So Nernst studies the variation of the electrode potential of an electrode with the temperature and concentration. With the temperature and concentration, the behavior of the electrolytes will be changed. Because we when study about the electrolytic cell, at that time we were talking about that with the temperature the conductivity increase, and that's why here the different idea will be there. So that's why E is equal to E degree cell minus 2.303 RT upon NF log 1 by concentration of the anode or cathode, that is written here. So this is the simple equation. Okay, here in place of R 8.314 and in place of here we can put in place of R 8.3 એટલે 2.303 તો છે જ multiply by 8.314 multiply by, suppose temperature we want to take about the room temperature, then that is the 298. Okay, and entire divide by the 96500, the which constant? Faraday constant. Then this all is going to answer give 0.059. That is our topic, and that here you can see this 0.059 is taken here. So entire Nernst equation is will be like this now. તો હવે આ Nernst equation ને આપણે આ રીતે પણ વિચારી શકીએ. So this will be the Nernst equation. Okay, now Nernst equation for cell. આ તો ખાલી electrode માટે હતું. તો Nernst equation for Nernst equation will be written in this pattern. So hope that you understand the revision of Nernst equation. Nernst equation you have to remember. Here also we are able to find out the value of Kc. So okay, so after getting this Nernst equation, we are approaching another topic, and that another is cell and then the conductivity. Okay, so here is the this topic will up to this only. Okay, bhai, where you can in previous case application we have find out into the form of the Kc. Now here delta G degree is equals to minus NFE degree cell. Doing these also you can find out the application of the EDC rail. Now from here we are going to start the our survey in another thing, and that survey will provide us that we are going to talk about the resistance. Okay, and what resistance say, let's study. You know what is resistance? Okay, so let's study what resistance say. So here is the topic of resistance. The substance which allow the passage of the electricity through them are known as conductors. Every conductor's material offers some obstruction to flow the electricity, which is called as resistance. It is denoted by R and measured in ohm. The resistance of any object is directly proportional to its length and inversely proportional to its area, and that we have seen earlier. Okay, so R is equals to rho L by A, where rho is the proportionality constant and rho is known as the resistivity, and the unit of this resistivity is ohm into meter. The inverse of the resistance is known as conductance. So here we can make another formula, that is of the conductance. G is equals to 1 upon R, where R is the resistance and G is there. So G is equals to 1 upon R, the conductance, and that's why the conductance unit will be the inverse of the ohm inverse, or in reverse you have to write mho. Okay, so that is our point of the talk. So that was our talk. Now I hope that you understand this point. So now we are entering in the another topic, and that another topic is conductivity. The inverse of the resistivity is known as conductivity, and it is represented by the Greek symbol kappa. The SI unit of the conductivity is Siemens per meter or Siemens meter inverse, or it is also taken in as the centimeter, because the rod we have taken are not so long મીટર તો બહુ લાંબુ થઈ જાય. We have to take only the centimeter. Why? That's why the majority units are taken as a centimeter. Okay, the formula for the conductivity is conductance multiplied by the cell constant. Now for measuring the resistance of an ionic solution, we need two problem first to resolve out. So which has two problems are occur. So these two problems are occurring due to the measurement of the ionic conductivity or the ionic resistivity. First is nothing but the passing direct current changes the composition of the solution, and second one is as a solution cannot be connected to the bridge like a metallic wire, that these two conduction problems can be the resolved by following these two taking. The conductivity cell, the phenomenon of the measuring the resistance of an ionic solution can be resolved by using the source of alternating current. DC current ના બદલે આપણે alternating current વાપરીશું, એટલે આપણે electricity વાળો. અને બીજું શું વાપરીશું તે એના માટે એક સ્પેશિયલી ડિઝાઇન સેલ વાપરીશું જે કોના તરીકે કામ કરશે, વાયર તરીકે કામ કરશે. So that is known as conductivity cell. So this is our prior idea about the conductivity cell. So now we are talking about the next thing, and that is known as molar conductivity. See, conductivity in the ion due to the concentration, with the increasing concentration what will happen with the conductivity, decreasing concentration what will happen to the conductivity, then these all ideas are known as the molar conductivity. So a conductivity cell consists of two platinum electrodes created with the platinum black. They have area of cross section A and area of separated by them is distance L. Okay, resistance of such a column of the solution is given by the R is equal to rho into L by A, but rho is equal to 1 upon kappa that we have previously studied. So in place of rho we will put 1 upon kappa as well. L upon A is known as cell constant, and which is denoted by G star. So here we will have resistance formula 1, and that will be the like this. So resistance formula we can write R is equals to G star upon kappa, and that will be the formula to remember also. Okay, now molar conductivity of a solution, it is defined as the conducting power of all the ions produced by the dissolving 1 mole of an electrolyte in the solution. So this definition you can write onwards. Molar conductivity lambda m is equal to kappa multiplied by 1000 divided by molarity. Here in place of m you can take C also, and unit you as well know, that is nothing but the Siemens centimeter square per mole inverse. Equivalent conductivity, it is the, if in case of concentration instead of molarity, if you are using equivalent, that is the node, then it is known as the equivalent conductivity. So molar conductivity and equivalent conductivity are the two part of the topic. Now we are entering the new topic, and new topic is also very interesting, that is nothing but the Kohlrausch law. Now Kohlrausch law for the independent migration of ions. Now we know that conductivity are doing due to the ions. Now ions are produced due to the adding of the electrolytes. Now there are two types of electrolytes, strong electrolytes and weak electrolytes. Which is separated out in maximum amount are known as strong electrolyte, and which cannot be separated out in maximum amount are known as weak electrolytes. So when electrolytes are added, they are get separated into the positive ion and negative ion. Now what happened with this positive ion and negative ion was studied by the Kohlrausch, and what it suggests that we are going to study in the Kohlrausch law. Kohlrausch law of the independent migration. According to this law, molar conductivity of an electrolyte at the infinite dilution can be expressed as the sum of individual contribution of the individual ions, that is positive and lambda negative. These are known as individual cooperation of the positive ion and negative ion, and if we will add both, then we will get the new answer. That answer is known as actually molar conductivity. So this is the molar conductivity, positive and negative ne plus કરી નાખવાનું, and we will get the molar conductivity idea. Okay, chalo, degree of dissociation. In the 11th standard we had studied about this. It is a ratio of the molar conductivity of at a specific concentration C jetla and infinite concentration. This is the dilution. At infinite concentration, that is the dilution. At infinite dilution we are knowing that it is limiting molar conductivity, and limiting molar conductivity is denoted by lambda degree m, and that's why we will have alpha is equal to lambda cm upon lambda degree m, and then last one is nothing but the dissociation constant, and you know the formula of the dissociation constant is nothing but the this, and you can do this by putting this answer.